Welcome back to The Explainer. Today we're diving into Episode 7, The Chemistry of Sight, Radiographic Film and the Sensitometric Curve. We're exploring an absolutely incredible piece of technological history, pulled directly from the BMIRIT curriculum that literally ruled medical imaging for a century. In this module, we're unpacking the precise physics of radiographic film, the chemical formation of the latent image, and how to quantitatively analyze film performance using H&D curves. Now, you might be thinking, hey, modern hospitals have all transitioned to digital, and you're right. But honestly, you cannot truly grasp digital signal-to-noise ratios, contrast, or spatial resolution without first mastering this foundational physics. Here's a quick look at our roadmap for today. We'll start with the anatomy of radiographic film, move to the latent image reaction, evaluate speed versus spatial resolution, map the characteristic curve, cover essential film storage protocols, and finally, wrap up with our key takeaways.
All right, let's jump right into Section 1, the anatomy of radiographic film.
So traditional X-ray film actually builds from the center out. It's kind of like a highly engineered microscopic sandwich. Right in the middle is this flexible polyester base, and it's intentionally tinted blue. Why? To reduce radiologist eye strain when they're staring at a bright light box all day. Moving outward, you've got a subbing layer that acts as a super strong adhesive, followed by the actual active magic layer, the emulsion, and finally the supercoat, which is just a thin layer of gelatin that protects all those sensitive inner layers from everyday handling damage. Now that emulsion layer is absolutely crucial. It's the active ingredient of the whole shebang. It relies on millions of tiny silver bromide crystals suspended perfectly within a gelatin matrix. And here's the clever part. By coating this emulsion on both sides of the polyester base, the film literally doubles its sensitivity. It catches exposure from intensifying screens pressing against both sides at once.
Moving right along to Section 2, the latent image reaction.
So what actually happens when an X-ray photon or a flash of screen light strikes the film? Well, it kicks off this microscopic, totally invisible chain reaction. The radiation ionizes those silver bromide crystals we just talked about. The freed silver ions then physically migrate to tiny structural defects in the crystal, which are called sensitivity specks. There, free electrons reduce them into microscopic clusters of metallic silver atoms. Boom, you've just created an invisible record of the patient's anatomy, the latent image. But here's where it gets truly mind-blowing. During processing, the chemical developer amplifies a single latent image site by an astonishing factor of roughly 10 to the 8th power. That is 100 million times. The developer acts as a chemical catalyst, turning thousands of surrounding silver ions into solid metallic silver. It takes an entirely invisible atomic change and transforms it into the bold, black, white, and gray image you can actually see with the naked eye. Which brings us to Section 3, Speed versus Spatial Resolution.
This crazy chemistry introduces a literal tug-of-war for radiographers. It's the classic dilemma, keeping the patient safe from radiation versus getting the sharpest possible picture. Film manufactured with larger silver halide crystals is considered fast. It gobbles up photons quickly, meaning you can hit the patient with a drastically lower radiation dose. The catch? It creates a much grainier image. On the flip side, smaller, fine-grained crystals produce beautifully sharp definition, but they're slow. You have to pump more radiation into the patient just to expose them. It's a constant, everyday balancing act.
Okay, on to Section 4, the characteristic curve. To mathematically map out this balancing act, we first have to define optical density. This is just a very precise measure of how dark the resulting film actually is. Mathematically, it's the log of the ratio of incident light over transmitted light. To put that into perspective, an optical density of 1 means only 10% of the viewbox light gets through the film. An optical density of 2? That means just 1% gets through. So we plot that optical density on the y-axis against log exposure on the x-axis. This creates a really elegant visual map of the film's entire behavioral profile. To gather this data, radiographers use a nifty device called a sensitometer. It perfectly exposes a strip of film to a precise step wedge of gradually increasing light intensities. The resulting characteristic curve maps out 3 distinct geographical zones. Down at the bottom left is the toe, representing severe underexposure, where the film is just way too light. Top right is the shoulder, where the film is absolutely blasted with exposure and goes totally black. But right there in the middle, that's the straight line portion. In this zone, a small change in exposure gives you a highly predictable linear change in image darkness. This straight line is our clinical playground. It's the useful diagnostic range. By analyzing these specific regions, you can instantly deduce the film's exact speed, its contrast capabilities, and your margin for error. If the whole curve shifts left on the x-axis, you've got a highly sensitive, fast film. The steepness, or the gamma, of that straight line portion tells you about contrast. A super steep line means high contrast, which is great for distinguishing bone from soft tissue, but it has a very short latitude. That means you have zero room for exposure errors. A flatter line gives you way more latitude, forgiving minor errors in your technique. We also always check the base plus fog, because even at absolute zero exposure, the film has a tiny bit of inherent density, and we want to keep that as low as possible. Let's pivot to Section 5, Essential Film Storage Protocols. Because we are dealing with a highly sensitive chemical ecosystem, how you store the film before use is a big deal. Strict adherence to storage rules prevents mechanical damage and accidental fogging that could completely ruin a diagnosis. Boxes absolutely must be stored vertically. Stacking them flat creates pressure artifacts that can actually mimic patient pathology. You've got to rotate stock strictly, first in, first out. Keep the film cool, dry, and entirely isolated from radiation and darkroom chemical fumes, which can slowly fog the film before it ever even sees a patient. Finally, let's wrap up with Section 6, our key takeaways. This snapshot, straight from the curriculum, beautifully anchors the core historical and scientific lessons we've distilled today, perfectly outlining everything from the anatomy of the film base to the sensibilmetric properties used to optimize your image quality. Let's do a quick recap to cement today's lessons. Physical structure directly drives chemical response, which we can then mathematically analyze and protect. It all relies on that dual emulsion silver bromide sandwich to capture the invisible latent image. Chemical developers provide that massive 100 million times amplification. We're constantly managing that clinical battle, where larger crystals reduce patient dose but sacrifice fine detail. Reading the H&D curve allows us to visually balance contrast and exposure latitude, and rigid storage protocols keep the whole system intact. So as we close out today's explainer, I want to leave you with a thought. The medium has completely evolved. We've traded darkrooms for digital pixels, but the underlying physics problem, it hasn't changed. A larger digital detector element today does exactly what a larger silver halide crystal did back then. It captures signal faster but lower spatial resolution. But here's the twist. With artificial intelligence now stepping in to actively denoise and upscale low-dose imaging, are we finally about to break the century-old rule that dose must dictate definition? It's definitely something to chew on until our next deep dive. Thanks so much for learning with me today.